we're here to talk about running inference, AI inference on EPYC. But before we go into EPYC, let's just talk about the entire optionality that AMD provides across enterprise needs, right? On the right-hand side, almost all the way to the right, is new Helios MI450 servers, the rack that we have introduced and we have announced. A lot of excitement around it. That's the one that you go to for all your training needs, the frontier models and everything, right? Next to it are Instinct UBBs, multiple Instinct GPUs on it. Then you have the AMD Instinct MI350P, which is a pretty hot product, and the AMD Radeon AI Pro products as well, right? And finally is the EPYC. So while we are here to talk about EPYC and inferencing on EPYC, we have the entire sort of gamut of options that you have to run from inference to training, everything that you need. What we'll do is in this talk today, we'll talk a little bit about what kind of models run on EPYC servers, why should you choose them, and some numbers and performance and things like that, right? So first, what are the type of workloads that are good for CPU AI or running on EPYC? So the first one's obviously very hot. Everybody talks about it today, generative AI, right? Generative AI, chatbots, summarization, translations. You want to ask a question like, how much vacation time do I have, right? You don't need a 70 billion model. You can run it on a very small model, which can run very nicely and efficiently on an EPYC server. So that's one. The next one is recommendation system. That's where the entire internet really lives on that, right? You get your product ads, you get your social media and everything. Some of you might have attended the Google talk here. They had basically one of the leading social media companies using EPYC with ZenDNN, with the products that we have for their recommendation systems. So that's sort of a cool thing that you can run on it. And very little gets talked about classical ML and deep learning, but this has been going on for forever, right? Fraud detection, risk assessment, diagnostics. These are the real workloads, if you will, that have been there forever. And all of this used to run on standard CPU servers. EPYCs are really good at that. So that's the whole spectrum of all the different workloads that we have. But why? Why would you do this, right? Many people have EPYC servers either on-prem or on the cloud, and they don't necessarily need to use all the capacity all the time. So you got your work days complete. There is processing that's possible at night. You can do large batch processing with the spare cycles that you have, right? You don't need to buy new servers for it. You just use what you have out there. But then it's not only about batch processing. In some cases, we have models which can run under 1 millisecond, lots of concurrency. You can get real-time responses as well, right? So you could do those kind of models too, right? The models are getting faster, CPUs are getting faster as well. Finally, we have many applications that run on your EPYC CPUs. And if you run AI along with it, you don't need to send data to another compute engine over the network. And so that's the other thing, that you can do it together between your application and the AI workload together. So that's kind of driving all the needs. Now, if you notice in this, I didn't say that, oh, because you didn't have a GPU, you should run it on EPYC, right? I'm just saying it that you could drive it because you could do it on EPYC, and EPYC is good for it. Now, one is CPU can run inference. That's good. I already talked about it. But can it run really fast? And that's where software comes into picture. So we talk about ZenDNN is a software that AMD has. It's sort of a DNN libraries. It's which can give you up to 2x performance uplift over native non-ZenDNN sort of software stack. It can run LLPs, LLMs, recommendation systems, and many more, right? Now, we built it with a plug-in approach in mind, right? We did not take it as a fork and take it. So with the plug-in approach, what is happening now is with frameworks like VLLM and Llama CPP, we are natively integrated. So you download VLLM and Llama CPP, ZenDNN is already in it. With PyTorch and TensorFlow, it's a plug-in approach. So you do get PyTorch and TensorFlow, and then you do a pip install, get ZenDNN, and run your frameworks with it, right? Now, this is only a 20-minute talk, so I can't go into all the optimizations that we have done, but there's graph optimizations, fusions, the low-level microkernels like the AOCL DLP, and in some cases, we might even use third-party libraries, right? Whatever works the best and gives you the best performance. We have implemented things like low-ordered APIs, and also an auto-tuner, which will tune it and use the best libraries possible for your workload, right? Depending on what you're doing. Now, there's a lot of work that is also going on in terms of getting low precision support, right? The quantization is at 4-bit and 8-bit. And what we're doing also now is we are actually quantizing the models and putting them back on Hugging Face as running on AMD EPYC servers. So that's kind of gives you a very high-level picture of what we do with ZenDNN. Some numbers, with VLLM itself is very good. It's one of the leading serving framework right now, runs very fast. But then if you do ZenDNN, you get 25% better, right? Then you do quantization, you get another 1.5 to 2x on top of it. So you could even run put it all together 2.5 times faster compared to just native VLLM, right? So using ZenDNN. Now, to make this all easier, we're also introducing AI skills on top of it. So this is in the AMD skills repo. You can download the skills. You can just tell you, set me up with VLLM and ZenDNN, and off you go. We're improving this to get more performance and things like that as well added on top of it, but that's one of the key things that we are working on. Software never stays at one place. So obviously, our latest release, ZenDNN 6.0, is available now. The biggest thing that we have done with 6.0 is actually to support Venice, which is our Gen 6 processor right now. But then that's not the only thing that we have done. We have also done other things, which is ease of use, which is to integrate ZenDNN with AMD Inference microservices, AIM Dockers. So you just get the Docker and run it, and then you have everything that you need. We did partner with Red Hat, and ZenDNN is also part of the OpenShift AI as well. Ecosystem moves very fast. The number of releases that PyTorch and VLLM does it's tremendous. ZenDNN supports the latest versions of those releases. And we also do weekly or fortnightly downloads, so that you can support actually the latest one that is at that point of time. I talked a little bit about quantization earlier, like low precision models, but the big thing that we did this time is FP16, because Venice supports FP16 natively, so that's something that got added in this release. And we always keep looking at what are the different kind of models that can keep running on EPYC CPUs. So now we are starting to introduce more MOE models. You see the graph with GPT OSs there, and it's sort of showing 2x the performance over Turin, right, our previous generation with Venice. But we keep supporting new models as well as we move on, right? So that's sort of all about ZenDNN and how to run software on EPYC and for getting better inference. I'm going to invite Milind to come and talk more about performance and sort of on the Agentic AI stuff. Thanks. Thank you.
Thank you, Sid. Wow, I don't know if it's Sid you or the title of the talk. This is a popular audience. I mean, more seats are filled here than before. Well, good afternoon. Welcome, everybody. Thank you, Sid, again. I'll talk a little bit about performance in the context of what we are seeing as relevant for Agentic AI. But before I talk about Agentic AI itself, I want to talk about a couple of benchmarks and use cases, starting with TPC XAI. Now, when we say AI, most people automatically think GPUs, right? Well, it's time to rethink that, especially in the context of what Sid presented on EPYC CPUs. AI is not just GPUs or training. In fact, the bulk of the use cases are dominated by inference. And CPUs, it turns out, are excellent at that. But then inference is just one piece or one part of the pipeline. Neither is training. We need to focus on the holistic pipeline for all of the use cases that closely mirror what an actual practitioner does. So TPC XAI was developed by TPC exactly to address that use case or that need. It's an end-to-end pipeline, analogous to what an actual practitioner will do. So it comprises many, many use cases, so 10 use cases to be specific, across machine learning and deep learning. And they mirror a lot of the real-world scenarios that you might see. So for example, sales forecasting or fraud detection, anomaly detection, all of these are included in the benchmark. And you can see towards the right, that column lists the main libraries that get invoked when you run TPC XAI. So under the hood, here we see multiple stages in the benchmark. I'm not going to go through every single one of them, but the basic premise is that you generate the data, you load it, you have a power training test, you have a serving test, and you have a throughput test. Now, folks who are familiar with TPC will know that this is a very similar model to the rest of TPC's benchmarks. And at the end of the benchmark run, we aggregate all of the performance into one single metric, which is shown on the bottom right, the AI use cases per minute at that particular scale factor. So we think this is an excellent proxy for what you need to run agentic AI workflows on your platforms. Now notice, just like Sid, I didn't say CPU platforms, I didn't say GPU platforms, period. So here we see a comparison of this benchmark's performance on a single node scale factor 30 gigabytes configuration. Now this benchmark also supports a much larger multi-node sort of configuration, but for the purpose of this comparison, we ran it on a single dual node Venice, Turin, and Granite Rapid system. We created multiple instances of a 16-core container, stacked up all the containers on the platform, aggregated all of the AIUC PM metrics, and in the end, what you see is that Venice simply blows the competition out the water. As a matter of fact, it's obvious that it also gives a very nice generational boost compared to Turin. So for agentic workflows, this is a good proxy because it's important, A, to focus on end-to-end workflows, B, agentic AI workflows are driving up CPU and GPU utilization quite significantly. So we need a benchmark that can show that. And CPUs are getting more diverse and utilized, right, across all of these workloads. So TPC XAI, 3x for Venice. The other subsection I want you to keep in mind when we are looking at agentic AI workflows is it's really split into two subsections. One is the classical machine learning methods, which are primarily your slightly older statistical methods, primarily FP32. And then I've picked similarity search as another representative bucket. So you can see, I'll show performance data for both of these sections for Venice versus Turin versus Granite. The goal here is to show that these common set of workloads that are used, these are the common operations and they form the bedrock of a lot of the applications that we use, millions of people around the world, whether it's e-commerce, online commerce, or recommendation systems, right? We all use these. So subconsciously or consciously, we are exercising the functionality of these on these platforms. So how does Venice fare? Well, I mean, the chart shows how good the performance uplift is for Venice versus Turin and Granite. But it's really a combination of the hardware capabilities that Venice brings to bear. The higher core count, the IPC improvements, the frequency uplifts, and the platform level improvements, whether it's advancements in DDR technology or the PCI Gen 6 that Venice supports versus competition, and also uplift from Turin. But in addition to that, AMD has made advances and significant investments in our software ecosystem. So a quick show of hands if you have heard about or followed AOCL. We have a couple, 3 hands, not as many as I would have liked. So AOCL is part of our suite of optimized libraries. It's open source, but from the show of hands, it feels like it's a better kept secret than we intend. So we really need to get that momentum behind AOCL and AOCC and our tools. But coming back to this, right? So the 4x and the 3x and the 2.5x improvements you see is really a confluence of the hardware feature improvements plus the underlying software optimizations we have made in our AOCL libraries, in the GEMS, in the Bliss and BLAST routines. So in the aggregate, whether you're looking at k-means clustering or PCA or regression workloads or support vector, all of these perform really, really well on Venice. The next subsection, I'll touch upon this briefly, is around similarity search. And you know, all of us have bought things online. All of us subscribe to at least one online streaming platform. So we are all familiar with the pop-up that since you bought this, you might consider this. Or because you watched this, you might want to watch that, right? All of that is basically coming from some sort of combination of similarity search coupled with them, the platforms, storing all of the historical information about your habits. So using similarity search as a good proxy for these on a couple of data sets. On the left, you see the Cohere Wikipedia data set that we used, along with its underlying methods of scans and index searches and so on. And on the right, you see a similar performance comparison for the SIFT 1M dataset. Again, the same sort of operations, right? And you can see that Venice delivers impressive performance gains across the board, whether it's method A versus method B, or dataset A versus dataset B. So the point is to drive home that this is really a culmination of how CPUs are evolving to address this changing paradigm. So up until now, you can think of the common chatbot type of model, where you have one or more human users interacting with a language model. So you're feeding in prompts, you're getting tokens back with the answers, and you're doing this iteratively. Now, in that workflow, a CPU is primarily used to host the GPUs, multiple GPUs in many cases. So the attach rate, if I can use that phrase, is one CPU to about 8 or 4 GPUs. So you would tend to think it's very, very heavily GPU dominated. Now, the picture on the right shows how the world has changed or is changing. And Agentic AI is driving a surge towards CPU-based workloads and implementations. So we are really transitioning to a diverse set of workloads, and I'll talk about what that diversity looks like. The incoming request still lands on what is called the inference cluster. From there, it makes its way to the application cluster, which is really running a diverse set of workloads. Now, some of these workloads are ephemeral. They can be deployed with very small number of cores per container, or they can be large containers that run for long. But the point is, it's not a one-size-fits-all. These workloads can include agents that pull assets, they can look up metadata, they can crawl web pages, they can search databases, they can do index searches, they can do RAG operations. So it's very, very different. They can pull log files. So there are agents that analyze code, analyze data, and everything in between. So the picture is changing from the one on the left, which is a 1:1 attach rate, to the one on the right, where the CPUs are no longer confined to just hosting the GPUs, but are actually doing the bulk of the work in conjunction with the GPUs. So the attach rate is primarily shifting towards a 1:1. So in closing, what I'd like to leave you with is a few things. We are probably the only company that can provide and deliver an end-to-end solution of hardware and software solutions. We have accelerators that go from CPUs to GPUs to DPUs and everything in between. CPU-based AI is growing rapidly, and it's really driven by the surge in this agentic world that we live in. In the previous picture, where we talked about the inference cluster and the application cluster, the workloads that land on the application cluster now they follow what we call the DPR-CV model. I shouldn't say we, I just dreamt it up about 15 minutes ago. So the request gets decomposed, then there is a planning and routing, and by routing, it gets routed to the accelerator that is the best fit for it. And then after the work is done by the agent, somebody collects all of that information, verifies it, and if needed, we run all of this iteratively. So the CPU platforms are a great fit for that. The real world and industry standard benchmarks that I used represent this really well. And finally, as Sid mentioned, AMD follows an open source software first approach. So it makes it really easy for folks like the ISVs and end users to tie it all up into one solution that fits your use case the best. Throughout this event, we have a number of pre-recorded videos and demos on stage. So I encourage you to meet us both at the Dev Zone and also walk around and take advantage of all these videos. And with that, thank you very much.